Hello everybody, this is Mr. Hoig coming to you with some notes on magnets today. We'll start with a little humor. Alright, so our EQ is going to be what are the basic properties of magnets and what is a magnetic field. So those two things are going to go hand in hand. So I'll give you a chance to write these down if you want to pause it for a minute. Okay, so we basically have two different ideas here. You got a magnet, which is a material that can exert this magnetic effect on other items, and then you've got items that are affected by it. So you've got a magnet that exerts the force, and then objects that are magnetic will react to that force. Some examples are bar magnets. Horseshoe magnets look a little bit different, and then you've got your magnetic materials with paperclip and nails and some other objects. So some things those have in common are they're often metals. A good example that we see quite often are refrigerator magnets. So the refrigerator itself is magnetic, and the magnets would be exerting that force on the refrigerator. Then we've got magnetic poles. There are two places on the magnet. They're north and south. This is where the magnetic field is going to be strongest, and it's also where the magnetic field is entering and exiting the magnet. It's always going to have at least one of each, North Pole and South Pole. Sometimes you can get weird shaped magnets that will have more than two, but it's always going to have at least one of each. So here's a picture that shows that. Even if you have one magnet with a north and a south, if that's broken apart, you can see at the break here, these two poles did not exist before. But since they broke in half, it becomes its own magnet, and every magnet has to have two poles. So since the south will carry down, then this becomes the new north pole, and this becomes this magnet's new south pole. And if you break it again, it's going to do the same thing, and it will continue to do that every time it's broken. There's three interactions between two magnets with these poles. The north and south poles will attract. They'll pull together, while south and south repel, north and north repel. So the idea here, you can see if the poles are different, they will attract. If they are the same pole, it will repel. So if we do some investigation as far as a magnetic field and how we can actually see that, we can use a magnet and some compasses to do that. So if we actually put compasses around our magnets, our north pole is going to face away, or excuse me, the north side of the compass will face away from the north pole. As you can see with all these green arrows, it's facing away. And then as you move the magnet around towards the south pole of the magnet, those compasses actually switch the other way, so they are attracted to the south pole. So north and north repel, so it points away, and then north will attract to the south, so it points towards. So these arrows will actually help illustrate how this magnetic field is going to look. And this is a drawing of that magnetic field. So if we would have our compasses, the north points away, and as we get closer to the south, it's going to point towards the south. So when we talk about a field, basically what that's saying is all spots around that magnet is going to have some measurable quantity um, of that magnet. So that attraction or repulsion, there's going to be some value no matter where you're at around that magnet. Magnetic field lines. These are lines that you saw before with the arrows that were going around the magnets. They point in the direction of the force. So these magnetic field lines always point away from the north and towards the south. So you can think of it as the magnetic field is coming out the north end and then entering the south end. And the reason why we have a magnetic field is due to electrons. We've talked a little bit about electrons already in the atom as well as with static. And they have an effect in magnets as well. And so these electrons actually moving around are what cause magnetic fields to occur. And just like you may have already noticed, opposites attract. So positive and negative, like peanut butter and jelly, salt and pepper. There's probably a lot of other things that you can think about here. But opposites attract, and things that are alike repel. So when we think about magnets, if it's north and south, that would be opposites, those attract. North and north, south and south, those are the same, so they repel. So in your notebooks, you can draw the bar magnet here with north and south pole, and then see if you can draw a magnetic field around this magnet. So if you want to pause it and do that quick. And this is what that's going to look like. So again, our magnetic field is always coming out the north end and in the south end. The two magnets, when we put those next to each other, we can use the same general idea that the magnetic field will come out the north end and go in the south end. But when the two magnets are close to each other, it's going to look slightly different because you will have the two magnets also interacting. So if you want to take a chance to pause it and see if you can imagine or draw what that would look like. Okay, so these magnets are different colors, but it's set up the same. North and south are pointing towards each other. So it will come out the north end, and in general, it will want to try to curve around to the south. But once we put this other magnet above it, it's going to try to curve around, and it's close to the south pole, and so it'll actually curve back to it. So that's where you get this interaction occurring and a slight bending of the magnetic field. Basically, everything on the bottom half of the magnet and the top half of the magnet is looking the same. The only thing that's going to differ there is you've got this field that comes all the way around the outside. So when you have two magnets, kind of the same general idea occurs where you've got the field coming out the north, in the south, but when you have those magnets next to each other, all of a sudden those lines start to interact slightly differently than you may expect. And this is an example of a different magnet here. So it's a little bit different than just our bar magnet. But again, we've got North Pole and South Pole. So if you want to try to draw that. So again, it comes out the north and goes into the south. So these basically interact straight between. And then you've also got some field that moves out this way and will loop all the way around and loop all the way around, come in the south end as well. And that's our show. So thanks for watching.